Alright, so I'll be presenting my part on AC circuits, which is the past, present, and future research. So from the past research and historical foundations, what I found out is that we have key discoverers, which are Michael Faraday and Nikola Tesla. So Michael Faraday, why he's important is because he had electromagnetic induction, which he kind of laid the groundwork for AC systems. So basically, he discovered the principle of electromagnetic induction, which is the generation of electric current by changing magnetic fields. Through this, his experiments like coils, wires, and magnets demonstrated that moving the magnetic field induces a current in a conductor, which is the foundation for electrical generators and transformers, which is actually the central principle of how alternating currents or AC systems work or transmit power. Another important person is Nikola Tesla, which is he basically patented the induction motor and the polyphase AC system. So Tesla patented his revolutionary induction motor, which operates using rotating magnetic fields and does not require brushes like the DC motors. He also designed the polyphase AC system, including multi-phase generators, transformers, and motors, making it possible to transmit electricity over long distances and efficiently. And the last person is Lucian Garland and John Dixon Gibbs, which they had the early transformers. They developed them, and basically the work on transformers enabled AC systems to basically get stepped up or down in voltage levels, reducing energy loss over long distances. And some technology milestones that I found out were in 1891, the first long distance AC power was transmission to Frankfurt, Germany, which marked a significant milestone in demonstrating how AC systems are practical for long distance energy distribution. And another one is in 1995 in Niagara Falls Power Plant, which was powered by a Tesla's AC system, which was one of the earliest and largest hydroelectric power stations. This basically demonstrated the economic viability of AC power generation and transmission and its role for global electrical systems. All right, next for our present research trends. So which I found out the research is smart grids, which are incorporating real-time monitoring and AI for efficient power distribution. Basically what this means is that it's incorporating AI, which is the better demand supply management, minimizing outages and efficiencies, and it's also integration with IoT devices, which are like smart appliances and stuff like that, which enables real-time energy usage and data collection for optimization. A new one is renewable energy integration, which is AC systems which are evolving to accommodate hybrid system setups like solar and wind energy, ensuring a seamless interface with traditional grids. So basically what it's trying to do is enhance inverter technologies, improve the efficiency and reliability of converting renewable DC and AC, to AC power for grid reliability. The last one is high voltage AC transmission, or HVAC. HVAC reduces resistive losses by transmitting electrical at high voltages over long distances, then stepping it down near consumption points. Basically what they're trying to do is they're trying to focus on sustainable materials for technologies like HVAC to make it more efficient and eco-friendly. And lastly is our future research directions. So what I researched is that they're trying to do superconducting AC lines, which superconductors which have zero electrical resistance at low temperatures uh, promise near lossless transmission of electricity. And the challenges include developing a cost-effective material and refrigeration system for urban and high-demand applications. The next one is wireless power transmission. So research in AC-based contactless energy transfer aims to enable wireless charging for large-scale devices, homes, and vehicles. So basically what they're trying to do is trying to have energy transfer through no wire. And technologies like resonant inductive coupling and microwave power transmission are being explored for that. And the next one is hybrid AC-DC grids. So combining the flexibility of AC systems with the efficiency of DC transmissions to basically create an overall grid performance. These grids are being designed to adapt dynamically to power generation and consumption patterns. And the next one is AI and grid stability. So predictive maintenance uses AI to anticipate faults and schedule proactive repairs, minimizing distributions. AI-driven optimization ensures real-time load balancing, enhancing grid reliability and efficiency. And these are my sources.
In a DC circuit, power flows in one direction, while in an AC circuit, power changes direction periodically, causing a sine waveform. Three components make up an AC circuit, a resistor which resists current flow, a resistor which stores power while resisting changes in voltage, causing a type of resistance called capacitive reactance, decreasing with high current. An inductor is a coil of wire which induces a magnetic field, creating inductive reactance. When changes in current occur, increasing resistance with high current. Impedance is the measure of all these resistances in an AC circuit. The phase angle measures the time difference between when voltage and current peaks. A positive angle means that voltage is leading, while negative means that the current is leading, and is measured in angles or radians. Average power is the instantaneous power measured over one cycle by multiplying current RMS by the voltage RMS. RMS stands for root mean square. Power factor, which affects the average power, is represented by cosine of the phase angle. If it is less than 0, it is absorbing power. If it is greater than 1, it is generating power. Resonant frequency is when the inductive and capacitive reactance cancel each other out, causing current to flow at a maximum. If not driven by a voltage source, the circuit would begin to oscillate. Finally, transformers change the voltage using induction, either by stepping the voltage up or down. This change is based on the number of windings from the primary side to the secondary side. The higher voltage is better for transporting power as it leads to less power loss, while lower voltage is much safer to use. And while the voltage is high, the current is low. And while the voltage is low, the current is high.
Okay, I'm going to be doing the two problems from chapter 15. And we're going to start with number 16. What is the capacitance of a capacitor whose reactance is 10 ohms at 60 hertz? And so the frequency is going to be 60 hertz. The reactance is 10 ohms. And we're trying to find the capacitance, which is C. So we're going to have to rework the equation in order to find capacitance. So in order to do that, we just put C on the outside and switch the two reactants since we have that variable, and we're going to find C instead. So it's going to equal 1 over the angular frequency, which is this equation right here, 2 pi times f, the frequency, which is 60 hertz, times the reactance, which is 10 ohms. So all of that is equal to 1 over 3,769.9, and that equals to 2.6 times 10 to the negative 4 as a capacitance. Now we're going to move on to the next question, number 30. The EMF of an AC source is given by the volt of this equation, where the initial voltage is equal to 100 and the the angular frequency is 200 times pi. So calculate the average power output of the source if it is connected across a 20 this capacitor, a 20 mH inductor, and a 50 ohm resistor. And so this is the equation that we have for the average power, which is the initial voltage times the initial resistance divided by 2 over the power factor. So for both A and B, the difference between the current and potential is this symbol right here, which is equal to pi over 2, and that's gonna make the power factor become 0. So when we have this is gonna equal 0. So basically all of these, this equation times 0 is still gonna be 0. So for both A and B, the answer, the power factor becomes, the average power is gonna equal to 0. Now for C, the difference between the current and EMF is 0, so power factor is 1. So this cosine of this symbol is going to equal 1. So now we have the resistance as 50, right? So we need to substitute that for the equation of voltage over resistance, which is equal to 100 over 50. So that's going to equal to 2. So since the power factor is 1, we're going to be able to solve the equation and putting the initial voltage as 100 times I, which is 2, over 2, that cancels out. So 100 times 1 is still 100. So that's going to be the power, the average power for C.